everybody, today we're going to talk about elasticity of demand and relative rate of change. To get us started, we're going to take a look at a few stock prices. So the first one here is MGM Resorts International, and I pulled dates that were close together. So this is about the middle of June of 2020. Shares were $18.21 a piece. By June of 2021, again in the middle of that month, the price of the share had risen to $40.86. So we saw an increase happen there. Let's look at another one. So this is Amazon, and same time period, so about the middle of June 2020, shares were $2,675 a piece. And then by June of 2021, that had increased to $3,486.90. So my question for you is, which stock went up more? That's what we're going to talk about in this section. And well, I think right now you're like, obviously this went 18 to 40 and this went 2,675 to 3,486. You can tell Amazon went up, but we have to think about perspective and how we want to talk about how the stock went up. So that's what we need to start with, is saying our answer to this question of what went up more is dependent on whether we're looking at a number versus a percentage. So relative rate of change is our first topic for this section, and I want to give you this definition. So the relative rate of change of a function is the amount that the function changed divided by what it was before. So we look at the change over the beginning. So it's important that you understand what goes in the bottom. I divide by where I started, not where I ended up. Percentage rate of change is really close to relative rate of change. It just means we multiply by 100. Relative rate of change will give us a decimal. So if I multiply by 100, now I get a percent. So you'll see it's the same formula, f of x1 minus f of x0 over f of x0 times 100. So let's go back. Let's go back to Amazon and MGM and look at what happened. So Amazon started at the 2,675, ended up at 3,486.90. That was a $811.90 increase. MGM went from $18.21 to $40.86, so that was a $22.65 increase. So there's our numeric thing. Numeric, it's easy to say, yep, Amazon went up more. If I turn it into a percent though, or into the relative rate of change, so the percent rate of change would be $811.90 divided by $2,675, so that's a 0.0, I hope you can see that there, times 100, said the increase we saw for Amazon was a 30.35% increase in the price of the stock. Let's do the same thing with MGM. So we saw that difference was $22.65, but we're dividing by 1821 times 100, said it went up 124.38%. So numerically, Amazon went up more, but if I look at the percentage, we can see MGM went up more. So how does that come into what we've been talking about calculus? Well, the relative rate of change was really change over original. And in calculus, change is the derivative. So what we're going to have is an expression of f prime of x over f of x. So the change, f prime of x, over what we had, f of x. Let's start with an example. We're going to find the relative rate of change of the price function. So my price function is p equals 3 plus 0.25x. We're going to plug in x equals 10. So I'm going to need two things. I need p prime and I need p. I can see p already, so let's figure out p prime. P prime is 0.25. Notice there's no x there, so there's nothing I'm going to have to plug into the p prime when I do my relative rate of change. But I am going to have to plug the 10 into the original function p. So let's do that. So I have p equals 3 plus 0.25 times 10. Now we're ready to put this together. I need to divide the 0.25 by 5.5. That gives me 0.03125 or 3.125%. So the first one where it's a decimal, 0.03125, this is what we would call relative rate of change. And then the 3.125 with the percent, then would be our percentage rate of change. Let's do that again. A model for the number of stores owned by a large convenience store can be modeled by the function f of t equals 0.18t plus 2, where f of t is the number of stores in thousands t years after 1980. Find the percentage rate of change for the convenience stores. Here's what we want to do. We want to take the derivative, divide it by the function, multiply by 100. Derivative of 0.18t plus 2 is 0.18. That becomes our numerator. The denominator is still 0.18t plus 2. I wanted to take the time to step us through, well, what do I do with this 100 when I'm not plugging in a number? It's probably good to think about maybe as a fraction. That way I can think multiply across the numerator, multiply across the denominator, but you're only going to multiply that 100 one time. You're going to do 100 times 0.18. That's going to give you 18 over 0.18t plus 2. Let's graph this over the interval from 0 to 40. Now think about what that means. T is our time in years, so 0 would be 1980. If I go to 40, if I add 40 to 1980, that'll put us at 2020. When I graph this, I'm not trying to graph this by hand. I definitely want to use technology, so we're going to go over to Desmos and graph this. So here I'm in Desmos. I'm going to do f of x equals, I have 18 divided by 0.18 x instead of t. I can't put t in here because Desmos is going to work with x's, so we know that already. We know that we always switch over to x. And then I say plus 2. Now something popped up on the screen, but we want to make it the part we want. So I'm going to set the domain. So I hit like a set notation. I hit 0, less than or equal to. I hit x, less than or equal to. And then I hit 40. So now I have said, here's the domain I want. So if I kind of scroll over, you'll see the start and the stop to it. So I can see it started at 0, it's going to stop at 40. If you kind of want to zoom in a little bit more than that, you could hit zoom in. I kind of like to go to the settings instead. And I can tell I need to see from 0 to 10, so that's what I'm going to do. On the settings, I'm going to say why I would like to go from 0 to 10. Let's look at another function. This time I have f of x is 3x squared minus 2 natural log of x. I take the derivative to start. I'm using the power rule. 3x squared becomes 6x. 2 natural log of x becomes 2 over x. Now that I want to make this the relative rate of change, remember we're going to take the derivative and put it over the original function. So I have 6x minus 2 over x divided by 3x squared minus 2 natural log of x. This is a complex fraction because I have a fraction within a fraction. What I want to do is clear the extra fraction. And the extra fraction is that 2 over x. I'm looking at that x in the bottom, and that's what's going to help me clear it. So I'm going to multiply everything by x. So this means I'm going x over x. You really want to distribute this, so like 6x times x minus 2 over x times x. This is like the long way, but I think sometimes the long way really helps you see what I'm doing. Okay, so here it is to everything. So the 6x times x, that'll be 6x squared. This x cancels this x. We cleared that complex fraction. We're going to put the x squared and the x together to get 3x cubed. And this x, I'm just going to bring it over by the 2 so you don't get it confused with the natural log. So it'll look like this. I have 6x squared minus 2 over 3x cubed minus 2x natural log of x. Don't worry, we're not graphing that one. Okay. So relative rate of change gets us ready for elasticity of demand. And what I think about with elasticity of demand is about things like Black Friday or Amazon Prime Day. What is it? It's about how does the price affect our demand of an item? So do we want it more if it goes on sale? Or if the price goes up, do we want it any less? So there's different things that we're going to buy no matter what, and there's other things that people get really excited about, right? Like the Amazon Prime and Black Friday Day where it gets a little competitive. Sometimes things go up and it also increases people's willingness to provide that item. So look at this just as in contrast to Black Friday where people are fighting over things. We have this idea that maybe you guys are familiar with, like surge pricing. So think Uber, which is what this is on here. Uber surge happens when we have a lot of people that want to use Uber, but there's not a lot of cars out there. So they increase the price. Increasing the price does a couple things. Hopefully it encourages more Uber drivers to go out and be there to provide that ride share, but it also maybe gets some people to say, oh, maybe I'm not going to go out, or maybe I'm just going to walk, right? So it can kind of decrease the demand of people wanting to take the ride share and hopefully increase that demand for people who want to provide the service. So we have a lot of things going on here with changing prices. So elasticity of demand looks at what happens when the price is increased. Will it go up or down? If the demand will go up, then decreasing the price will increase the quantity sold and hopefully thereby increase the revenue. If the demand will not go up, then the only way to increase the revenue is to increase the price. If the demand will go up, but the revenue goes down, this means we shouldn't change the price at all. Again, our idea is we want to have big revenue, right? Hopefully bigger revenue means bigger profit. So this is what we want to think about, are these different scenarios of what happens when we change the price. We do have an equation that we're going to be using. It's called E of P, so E for elasticity. It will be negative P times F prime of P over F of P. So the negative P is that price. The negative is because, like, if you look at this demand, it's going down. So if we talked about how is it changing, it's decreasing, which is negative, which is why this negative is in the equation. It's just kind of to counterbalance it and give us positive answers. We will have three types of elasticity. So the first one is if E of P is greater than 1, the demand is elastic. A decrease in price will increase the demand. So we want to lower the price to increase the revenue. Second type says E of P is less than 1. So demand is inelastic. This says a decrease in price will not increase the demand. So what are they going to do? We're going to raise the price. This happens all the time. Think about streaming services like Netflix. They have to raise the price sometimes to cover their expense, and they're pretty sure that we're still going to buy it anyway. Our third choice is if E of P is equal to 1, then demand is called unit elastic. Any change to the price, either an increase or a decrease, will decrease the revenue, so you don't want to change the price. For sure, we need some examples. We're going to start pretty easy. I have X equals F of P is 10,000 minus 190p. Every time we do this, we'll start with finding E of P, so we just want to start with our generic formula. Then we'll plug in some numbers and say what's going on. So starting with E of P, I have negative P times F prime of P over F of P. So this is what we'll do each time. Negative P, there's nothing to do. The derivative, 10,000 is a constant, negative 190p gives me negative 190, and then I just rewrite 10,000 minus 190p. Okay. Negative negative is positive, so I have 190p over 10,000 minus 190p. Now let's look at our two numbers. We have E of 20, we also have E of 25. So we're going to take 190 times 20, and we're going to put that over 10,000 minus 190 times 20. I'm going to do numerator, denominator. That might help also. So 190 times 20 gives us 3,800. 10,000 minus 190 times 20 is 6,200. Now I could put this in the calculator. I can get a decimal, which is like 0.6, but we really don't have to, because the question really is this greater than 1, less than 1, or equal to 1? 38 over 62, could drop the zeros, right? 38 over 62, less than 1 says inelastic. So inelastic says we should raise the price to increase revenue. So we're going to go from 20 to 25. At 25, I have 190 times 25 over 10,000 minus 190 times 25. 190 times 25 is 4,750. 10,000 minus 190 times 25 is 5,250. Okay, again, what happened? I can look at it and see this is less than 1, so we could, again, raise the price. Let's try a different function. This time I have X equals F of P is 875 minus P minus 0.05 P squared. We'll find the elasticity of demand. We'll plug in 50, 70, 100, and interpret. Start with E of P is negative P. The derivative, 875, derivative is 0. Negative P gives me negative 1. Negative 0.05 P squared, the 2 comes down, that's negative 0.1 P, all over 875 minus P minus 0.05 P squared. To make this easier as we go, I am going to distribute the negative p. So negative negative is positive p, negative negative is positive 0.1 p squared over 875 minus p minus 0.05 p squared. Okay. Now we want to find E of 50, E of 70, and E of 100. Because we're going to do this 3 times, let's plug that into Desmos, not do all the work by ourselves, and see what we get, and we'll write the answers back over here. I'm going to call this E of x. Thinking about elasticity, I'll say equals parentheses. Now we have to put in x's instead of p's, so I have x plus 0.1 x squared. Notice I put parentheses because these things are both in the numerator. And then I'm going to divide by 875 minus x minus 0.05 x squared. Now I'm going to hit the settings, and I'm going to say please make a table, and it's going to put in values, but we're going to change those values to 50, 70, and 100. All right. 50 says 0.43, 70 says 1, and 100 says 4. Let's put that back on our other page, and we'll talk about what that means. 50 said 0.43. 0.43 is less than 1. This is inelastic, which says raise the price. 70, we got 1. That's unit elastic. Don't change the price. 100 gave us 4. This is greater than 1, which makes it elastic. And that says lower the price. So at 50, the price was too low. We wanted to increase it. We increased it to 70, which turned out to be perfect. When you get unit elastic, that means it maximizes the revenue. Kind of shows that 100, if you got a little greedy and made it higher, that's too high, and you're going to have to bring the price back down to maximize your revenue. Let's try a function that includes E. We're going to find the elasticity of demand given x equals f of p is 900 e to the negative 0.25 p. Then we'll put in the prices of 8, 6, and 4. E of p will be negative p times the derivative. I have 900 e to the negative 0.25 of p times the derivative of the exponent, negative 0.25, all over 900 e to the negative 0.25 p. So what do I see here? I see a negative times a negative is a positive, so I'm going to do p times negative 0.25, and it's going to give me positive 0.25 p. The 900 and the 900 are the same. The e to the negative 0.25 p and the e to the negative 0.25 p are the same. Those are going to cancel out. So I just have this nice little 0.25 p as my elasticity of demand. So let's try that with our 3 numbers. I have 8, I have 6, and I have 4. This time I think we can do it without the calculator. If I do 0.25 times 8, this is going to give me 2. 2 is greater than 1. This says elastic. Elastic says decrease price. So we decrease it. From 8 it went to 6. I have 0.25. If we multiply by 6, we get 1.5. 1.5 is still greater than 1. This means we are still elastic. And again, we should decrease the price. One more time, E of 4, 0.25 times 4 equals 1. Well, that's unit elastic, which means don't change the price. In general, we wouldn't want to keep just picking prices and seeing what happens if we should go up or down. What we would want to do is be efficient and try to figure out what price we should charge. So in this example, we have use the price demand equation, p plus 0.004x equals 32 to find the values for which the demand is elastic. First thing that needs to happen is rewrite this equation. I need to solve it for x. I'm going to have 0.004x. Equals 32 minus p. Now let's divide by 0.004. So I divided each of the two terms by 0.004. 32 divided by 0.004 is 8,000. And then I'm going to do 1 divided by 0.004, and it gives me 250 p. Now I can do the elasticity of demand is negative p. Then I want p prime. Well, I had 8,000 minus 250p. The derivative is negative 250 over 8,000 minus 250p. What do we want to do with this? We would like to set this equal to 1. I'm first going to simplify that negative p times negative 250p is 250p. And then I'm just kind of like cross multiplying. So I'm bringing this 8,000 minus 250p to the right. Let's bring the 250p over to the left. So the negative 250 on the right comes to positive 250 on the left. We have 500p equals 8,000. So our last step is divide, and it says the price we should charge is 16. So we didn't have to put a number in and see, should we go up, should we go down? We said this is our goal, we should sell it at 16, and that'll maximize our revenue. One last one, use the price demand equation Q equals D of P equals the square root of 325 minus P to find all values for which the demand is elastic. Now this one's written slightly different. Instead of an X, there's a Q. It means the same thing. I want you to be able to switch variables and be okay with it. So let's start by rewriting the square root of 325 minus P as 325 minus P to the 1/2. Then when I take the derivative, and let's go ahead and do that over here, I'm just going to call it X prime, I would have a half. I would have 325 minus P raised to the negative 1/2. So I'm doing the chain rule here. I brought the half down, I subtract 1. Don't forget to go back inside to the 325 minus P and put a negative 1 in. Here's our derivative. So now we can go to E of P equals negative P. I have 1/2 325 minus P to the negative 1/2 times negative 1 over, let's write the square root of 325 minus P. So let's write this kind of as a fraction and put things where they go. So the negative 1 times the negative P, that belongs in the numerator, that's a P. The 1/2 says you could put the 2 into the denominator. This negative 1/2 also belongs in the denominator. Remember that 1/2 is a square root, so this part, this first part, when it goes in the bottom, it's the square root of 325 minus P. Now this is the part where this gets okay. I also have the square root of 325 minus P already in the denominator, so let's put that in with it. So what do I have now? E of P equals P over 2 times 325 minus P. What were we trying to do? We wanted to find out when this is unit elastic. So we want that to be equal to 1. We're going to say P is equal to 2 times 325 minus P. Let's distribute. I have P equals 2 times 325 is 650 minus 2P. Let's push that over. So the 2P comes to the right. Now I have 3P is 650. Divide by 3. Says the price is 216.67.